meeting is being recorded.
Very good evening, everyone. I hope you all had a refreshing break and are ready for an engaging and informative session ahead. As we move forward in our exploration of quantum technologies and their integration with AI, we have a fascinating topic lined up for session 7, quantum machine learning in context to using cybersecurity. Cybersecurity has become one of the most critical aspects of our digital lives, and quantum machine learning holds the potential to revolutionize how we address security challenges in the digital era. This session promises to provide valuable insights into how these cutting-edge technologies converge to enhance cybersecurity frameworks. We are privileged to have with us Dr. Anup Girdhar. Dr. Girdhar is the CEO and founder of the Security Solutions and Technologies and serves as the editor-in-chief of both the Cyber Times newspaper and the Cyber Times International Journal of Technology and Management. With 23 plus years of professional experience, he is a renowned cybercrime investigator and cyber security consultant. Academically, Dr. Girdhar holds an MCA, MPhil Computer Science, PhD Computer Science, and professional certifications including Certified Ethical Hacker, Sun Certified Java Programmer, and Microsoft Certified System Engineer. He has been honored globally for his contributions to the field of cybersecurity. Dr. Girdhar is a technical board advisory member for information security courses at IGNU and certified cybersecurity professional courses at TMB Pune for both postgraduate and undergraduate levels. As an international trainer, he represented EC Council at Hacker Halted 2010 in Singapore and developed the Stability operating system on the Linux platform. He is also a member of prestigious organizations such as Computer Society of India, International Cyber Threat Task Force, Association for Computing Machinery, International Association of Engineers, and International Association of Computer Science and IT Singapore. He has delivered training sessions to institutions like the CBI, CID, ATS, and the Indian Army, and has been featured in leading national media outlets including the Times of India, Hindustan Times, Dainik Bhaskar, G News, Sahara News, and All India Radio. As a research guide, Dr. Girdhar has supervised MTech, MPhil, and PhD students. His area of specializations include cybersecurity, cybercrime investigation, cyber forensics, Linux administration, secure web development, secure code writing, cloud computing, open source development, digital marketing, virtualization, and cyber laws. He continues to make significant contributions to the field through his research, publication, and training initiatives. Without further ado, I invite Dr. Anup Girdhar to take virtual stage and enlighten with us his expertise on quantum machine learning in context to the using cybersecurity. Over to you, Dr. Girdhar.
Thank you so much, sir. Am I audible?
Yes, sir. Yes, sir.
Yeah. Thank you. Thank you so much. Thanks for great interaction and my details you have already shared to all the participants. So it's indeed a pleasure to be a part of your organization, sir. And I really appreciate the way you people are organizing various events, especially like FDP and all. So it's really great. And again, it's a privilege for me to be a part of such events. So thank you, first of all. And thank you, participants, for even I would say to join such kind of things that you are really interested to talk and to discuss about various other aspects of cryptography, quantum computing, cybersecurity. So we have various good topics I think we can talk about. And I would like to talk some details. Luckily I was indulge in one of the topic where the quantum is one of the part, and I'll share my personal experience in that particular part, in that particular regard as well. So quickly, I think let us start the topic. I would just share my screen to all of you first of all. Whenever we talk about the concept called quantum, what do you mean by the concepts called quantum, and what is this topic like quantum computing? And have you ever heard about uh, specifically certain algorithms, which are the cryptographic algorithms which are connected with quantum these days? And what are the next level challenges? Basically, there are a lot of challenges comes across. So what are the common challenges coming at in this regard? So we will talk about various aspects, and one of the algorithm where I personally indulge into, and we are working on that model. I have to talk about it. Yeah, now my screen is audible and visible. I hope I'm audible and my screen is visible, right?
Yes, sir, your screen is visible. Yes, sir.
Yeah, perfect. Perfect. Thank you. Okay, so we are talking about the concept of quantum machine learning and the context of using the cybersecurity. This is what the topic is all about, and we are going to share various different aspects about quantum, and in fact, we need to correlate various things altogether. Today, I think you are aware of the area where we're talking like a huge data, bulky data. In fact, we are talking about data collection model. In fact, today all the tech giants are today greedy about your data. So that's what the people are doing. They are working based on some machine learning algorithms. They are collecting your information, and they really want to analyze your information so that further they can go and although it is a privacy breach, that's another concept altogether. We need to understand what this issue all about. All the giants. Today, I believe we all are using Gmail. So if you really use Gmail, really, I would say think about how we can stop using it. Although we can't, because today your Android devices are connected on Gmail, right? You can't access your Android devices unless and until you don't have Gmail, right? Another concern is even we are on social media, social network sites. You're on Facebook, Twitter, LinkedIn, Snapchat, various other prospective sites are there where they are not charging you a single penny, and we are very happy to use their services. What they will do there with those services, have you ever think about, have you ever tried to analyze what are the real concept of this digital era? In other way, today I would say it's not only digital era, this is a data era. So today, even you keep 1 kg gold physical in the form of a tangible product, keep it somewhere. I believe at least knowledgeable person would not pick that product, because probably income tax would be behind you or some other thing that how you got this kind of products. But today, every IT expert or even other organizations, even managements from various different even Sensex listed companies, they are personally going to adapt your data. They want to collect your data on their cost. So why they are going to collect your data, what they will do with your data? So first and most important part, the basic concepts of machine learning also is there, that we need a data, because without data we cannot proceed. We cannot go for analytical models, various business analytics. I'll share some case studies also along with you, so that you can understand what is the real concept behind it, right? So we have a another aspects, and how quantum computing is basically trying to boost your information, how it react on the security models, on the standard, or I would say now that has to be a legacy of the security algorithms is now more or less in danger, right? Because of the concept of quantum computing. So hacking again supports quantum computing, and cybersecurity also supports based on quantum computing, because we need a technology, we need certain aspects. So I'm going to talk more on those regards. Right, this is all my area. So I remember I started my career at the time, once there was a 8-inch floppy, then 5 1 by 4 inch floppy, then 3.5 inch floppy, and we used to keep the data over there. 360, I believe 360 kilobytes was the space also available on 5 1 by 4 inch floppy. Right, can you imagine? 60 kilobytes, one floppy would be there like this. So we used to keep the data, and we had a collection of floppy boxes, and we used to keep such data at that point of time. Even that is more than enough for us. Slow and gradually we move across, and in last 25 to 30 years I have seen personally technology. Even you also know, like, technology like anything. Today, even your pen drive would be, I believe, around 256 GB, or and even more than that. Right. So what is the concept? Even your RAM, I personally work on 640 kilobyte RAM was there, which is the maximum RAM over there in the machines. Means 80586, 8085, 80286, 80386, 486, 586. Then Pentium series comes across. That was a technology where I have seen personally. I deployed those machineries in the government departments long back. So today we are talking about IoT. Today we are talking about the gadgets from where you are actually going to generate a lot of data. So you are talking about IoT. We are talking about now to storage. We talk about big data. So distributed data models are available. We talk about concepts of like bitcoins or cryptocurrencies. So for that we have a blockchain models, where you can have a huge transactions to be kept on the machine, and we need to process that data with an instance. So how could we process that instance? Means recently I'm working on one of the project. I'm actually on that particular project. So I just take some time from the people that I actually want to interact with all of you. So I just came out of that project. Right now the things are still going on. uh, in that particular project, what is the problem which I have seen? We got GBs of data in a minute. Can you imagine? So our one of the application is generating the data in such a way. You can take it like telecom, you can take it like the log servers. The log servers, like we are working on one of the sim tools, that is security event and incident management tools, information management tool. Right, so we need to generate the results on that basis, but the problem is uh, concurrent I believe there are 20,000 users, concurrent users on my project where I'm personally working, and each user is using somewhere 40 to 50,000 threads. So each request is basically working on 40 to 50,000 threads in each user, and in the same way we have 20,000 concurrent users where they are going to generate the huge level of data. So this is what the personally I'm working on one of the project. We deployed 25 servers with high GPUs. Can you imagine? The server frequently, down, it crashes because of heavy load. It seems to be like a DDoS attack or something like that. So this is what the real time issues where I am seeing. I'm monitoring and working on that particular model. So what would be the next level of solution? We applied CPUs, leave CPUs, all servers, 25 server for one application where I am personally deployed. Now I feel 25 is very very less. Somehow I need to either increase the number of servers or in last, or otherwise, although this technology, I would say, a little new one for everybody, so quite expensive. So before, every organization have their own budget, so that's another level of problem. But if you are not constraints with the budget, then the right solution is again quantum computing. How come we come into it? What is the scenario? Let us understand first of all what is quantum. let's say the classical feature of this quantum. Okay. Now, if we go into the binaries, bits, so it always represent with zeros and ones. While in case of quantum, we talk about qubits. So what are qubits? Qubits to be represented like you can say theta or one symbol you can see at this time to represent either the value 0 or 1 or both simultaneously. It means it is basically the in other way you can say uh, we have a matrix sort of, where now we are talking about a nth dimensional matrix. You take it like that, nth dimensional matrix, right? I want to take you into that direction. So first you take it like the qubits to be represented in the form of zeros and ones or both simultaneously. Both are combinedly required, so you can say it is multiple level of input, parallel processing, and multivariant results. Multivariant outcomes are there, and multivariant outcomes to be again re-evaluated, again refiltered, and it's again a chain process. It's a cycle sort of, where we have to calculate and we have to generate some outcomes from that particular perspective, where lot of internal processing model is there, lots of modules are there, and each module actually required one good server to perform. So this is what the purpose of one of the project where I personally indulge right now. And I'm facing a very means finally I'm a consultant actually to various corporate. So they are facing one of the biggest challenge, and we are there to identify what are the challenges and how we can mitigate those challenges. So we are onto it right now. So think about quantum now, how quantum computing will actually gonna solve our problems in this regard, to solve the high complex problems in the seconds versus years using a classical computing model. Years, why I am saying years to be there. uh have you heard about RSA algorithm? Even if we'll talk about some form of cryptography, so you can understand RSA. I remember we deployed RSA algorithm in one of the project almost I think 15 years back. So we deployed RSA algorithm. At that time we applied 32 bits RSA algorithm. Today we have 8K, right? Or even more than that. 8K is still working and practically implemented. 32 bits encryption algorithm, and the moment we applied on a highest performance server to we applied a brute force or dictionary attacks on that particular RSA algorithm to decode the approximately calculation time identified on the highest server. This is one of the practical which we have done, and I'm telling you on that regard. I identified that was 2 into 10 raised to power 56 years. So can you imagine what I'm talking about? 2 into 10 raised to power 56 years was a time uh, analyzed by the one of the highest server to just to apply the brute force attack to decrypt RSA. Right, RSA, Rivers, Shamim, Adaman, and that was 32-bit, one very basic, it was already decoded, right? Then 64, 128, 256, and slow and gradually it increased, and today people are using 8K 8K RSA algorithms. So think about that level, high complex problem statements are there, high problem statements where we people are working onto it, become the essential of big data processing, obviously, where you keep such data. Today, according to you, whatever you people are doing, wherever you indulge into, whatever your activity is all about, right? I believe you are on on mobile 24 by 7. We are doing a lot of various other activities frequently, right? Do you know all these exercise, all these activities being monitored, captured by all the applications which you deployed in your mobiles? I can show you today if you want. I'll show you how. Means yesterday night, which video you watched, what was your geolocation, what the application, what are the number of applications you accessed at what time. If you want, I can show you each and everything. Shall I hack your phones today? Do you really want something like practical like that? So I'll try to show you in that form as well, right? So concern is, if you think about it, is possible. So it means now you just try and analyze one user who and even there is a report also, one of the survey being committed, and it has been identified in India. People used to swipe on mobile, people used to swipe, the average daily swipe was somewhere 256 times. So 256 times daily, averagely, Indians are swiping on their mobiles. Can you imagine this? 256 times. So what activity you are performing, and along with that, the other metadata or artifacts are there in terms of forensics, which we use to capture the data, we identify or we analyze that data, we are working on that data. And think about one user almost generating GBs of data daily. And how many users are there in India? Means according to telco, if I am not wrong, recently I have seen somewhere one I was in one conference. So in that conference they said almost 300 crore sims are running on 140 crore population in India, average 140, 50, whatever, right? So averagely 2 sims per person is there which is running in India. Hardly matters. Probably there must be some families who do not have a phone, or they have one phone in their family, or such persons are there who might be carrying 884422 phones in their pockets as per their need. So I'm not talking about that, but the average is almost 300 sims. So 2 sims per person is going on, and each sim is itself is an identity, and that identity is actually generating the data in the versatile model, from the SMS, from the mobiles, from the geolocation, from the application which you are using, the link which you access. So I want everything, so that we can do behavioral analysis, your sentiment analysis. We can do various AI or machine learning based algorithms, and artificially will try to create a model, and that model generates some results on that basis. So this is what the purpose where we people are working. And even the tech giants are working, and think about how they collect the data and how we really represent that data, right? So meanwhile, classical computing is better for everyday task like email and all, that is fine. But for that, obviously you don't require a quantum computing, but quantum itself is something else. So I just explained what is qubit and how it comes into the picture. So most quantum computers are large and have to be kept near absolute zero. So you need to understand the physics, quantum physics, like what is absolute zero and how it rotates and how it carries the data over, uh, you can say 360-degree dimensions. And we need some basic values and to be calculated in different dimensions. The fastest publicly known quantum computer is 66 qubit. That is again located in China. So the people are there who are working onto it, and they generate the data. Few of the organizations, especially cloud computing organization like AWS, Microsoft, Google, they came with a cloud computing, and in case if you people really want to do or implement any high complex algorithms you want to implement on cloud, you might get that cloud servers. On a cloud you will get a quantum servers, I would say, on rent, on pay as you go model. By using that model you can apply and you can get those at least servers. So at least you can test, being a faculty, if you have any project, you are into the research. So I think you can get into that and you can really find a wonderful model, wonderful results on that basis, right? You can try at least on that model. So commercially it is quite available. For certain years it has been available, and you can process that. So in terms of security, if I connect cyber security with quantum, then QIS, as I told you, SIM tools. We are working on SIM tools. Now, what is SIM tool? You can just explore SEIM. You can understand what I'm talking all about. So there are certain products of the SIM tools that, suppose I have a mail server, I have a web server, I have any application, web-based application which is running on my backend. I need to analyze it. I need to understand the model. I need to take some management or technical decision. For that, I need some information science. I need information systems. But that information systems chokes, hangs, and even the technology itself generated DOS attacks. Can you imagine? It itself generates a huge level of data that processor chokes at that certain stage and cannot able to perform like anything. So that is the deadlocks. I hope you heard about deadlocks, right? So I'm talking about deadlocks generally you heard in databases. But now I'm talking about data processing deadlocks, because you have an ample of data being shooted in particular instance, and in that regard your system chokes, hangs, crash, reboot, kind of impact of such data, right? So itself called as a DDoS attack, sort of, or you can say land attack, or various other types of attacks, which Smurf attack and all that comes, some network attacks, sniffing attacks. So various attacks comes in that particular regard. So we need basically information systems or event management systems. So we have a SIM tools. But today, can you imagine if your organization have a 3000 computers, okay, and each computer is generating their activities because you are accessing every single thing on the system, and we need to generate those logs, and we have even not GB is less, we have a TBs of data per day. And then further we need to further analyze, we need to understand the monthly reports, we need to work on it. Huge servers are about to crash and it's still crashing. So we reach to the maximum limit of all such existing algorithms, which where we all are working all together, right? We talk about like in machine learning you have supervised, unsupervised learning, and various other algorithms. You just talk about, reinforcement learning. But how learning will goes across, where the data is frequently changing, and not only frequently changing, it is generating, it's updating, and we need to sanitize, collect the data, process the data. We need to aggregation, we go for a data aggregation. After data aggregation we go for a data transformation. After transformation we'll check the quality test of those data, and in case if data quality is okay, then only we'll keep and we'll apply that data on the existing models of machine learning, right? So there, once you apply that data on that machine learning, would really really create a problem for all of you. At that time your machine learning would, again, you can see the epochs and all the stages. Once you run that uh, the codes or your data to be immediately change, and the results could be changed. Even chat gpt, the day chat gpt came into the public domain, before that there was a report that chat gpt, they started with the 98% accuracy in their beta testing or alpha testings, right? So they already have the report of 98% accuracy of that system, and the day it comes to the public, within 2 days that accuracy dips up to 2%. Means where is 98%, where is 2%? It dips to 2% accuracy. How come? What happened? Because now you got numerous data, you got huge number of values and huge number of requests from the networks. So that was a what's a real concern. We think about that level of challenges. So if you really work on these challenges, I think you can understand what I'm talking all about, and you can realize what the type of data I'm talking, right? And that also crash for certain few days, for the initial days. But yes, slow and gradually they upgraded their data, and finally they also come to the computing like quantum, information science, quantum. Then we have a quantum cryptography. So focusing on exploiting the quantum physics for secure communication and secure computing. I believe, if you know, might be I have you have seen somewhere, telecom, Ministry of Telco, they already introduced one bid, open bid for all the academics. It was open for academics and startups and other enterprises, that please come with your quotation, and with a very huge quotation, right? They are ready to accept those quotations, where they want to handle the telco transactions based on one of the algorithm called QEA. I don't know whether you heard that or not, but I'll explain what is QEA and all that algorithms. So there was a quotation, and I was one of the part of that quotation with one of the academic to introduce, and probably they are very soon, they have already gone through one round or second round, but the decision is still pending at their end. Once it's being done, probably they'll get one of the academic, they will get a one government project, right, telco project, only and only on quantum, and they are going to give the complete access of quantum servers, right? So think about the level which I'm talking about. I'm talking this again in Delhi NCR, right? So this happened already, and just I think in the month of October, November, we filed this complete quotation to telco, with the relation model between industry and academia, sponsorship model. And being an industrial person, I was indulged, and one of the academic, one of the institution, university to whom I was associated. So we both presented that complete quotation to Government of India, especially in Ministry of Telco. So these are again, it's completely on quantum distributions and all. So that is quantum cryptography. Quantum cryptography. Think about how cryptography is coming across and what are the real challenges. Post quantum cryptography. Now, this is another model. Cryptography, where we are having a raw data and we applied a data to secure, we applied some cryptographic algorithms, right? And we have a key distribution model, two factor, you have a asymmetric key model. So you have a key distribution model, symmetric or asymmetric, whatever. So you have a key distribution models. So once you share the keys and you generate the keys, think about OTPs. Let's think about a authentication model. For every user, you got a OTPs, and that could be unique, completely unique for every user, uh, whenever you are going to make any transactions. So OTP is again the 3D transactional model from the banking system. Now, can you generate the unique OTPs? Now, come on, it is not possible, because think practically, your OTPs are again on 6 digits, right? Maximum 6 digits, 4 or 6 digits, in fact. So 6 digit means starting from 0000000 till 999999, right? So total number of combinations are very less. And how many transactions going on across a day? So if we really calculate the things, can we able to generate the unique code? Not possible. Unique code is not, it's not called as a unique code. That's what, it's a time management, session management model being imposed, those algorithm imposed in the these verification codes or QR codes, or even OTPs, one time passwords, right? So we need sometimes post quantum cryptographies also. So there are certain protocols available for solving such mathematical problems, rather than any physics, quantum physics model are interactable for the both quantum and classical computing, right? So these are the areas you can understand how it get into it. Cryptographically relevant quantum computer. So now it's not only data processing, it is like encrypted data processing. Now encrypted means, did you ever heard about the concept like called end-to-end encryption? I hope in WhatsApp you all are having the concept of end-to-end encryption. And how many chats are being produced by WhatsApp on a daily basis, think about. So did you ever work on social media analytics where the data is completely encrypted? So where are the artifacts? So first challenges even to collect those artifacts, to analyze those artifacts. Second, or you will have some certain duration as a sample you collect. So corpus, you, I hope you heard about the word called corpus. It's a collection of huge data information, and which we need to process and we need to index sometimes. This is how big data works. And we index that data, and after indexing we'll have a keywords, and then instead of accessing direct data, we'll access index. But now the index, the size of the index itself is a very huge, very huge. So we can't work directly onto it. That's another problem, right? So we want a data which is again highly complex data, the size of the data, each data packet again in the form of mbs or gbs, and volume, billions of transactions going on across within an hour, billions of transactions are going. Such projects are there. How you can handle the encrypted data? And let us assume I want to have entire data of your organization where you have end-to-end encryptions, where you are talking about a key distribution model, where you have wi-fi. So how your wi-fi is working, that the data is being transferring through internet, through wi-fi, and that packet is all packets are encrypted. I hope you heard about wpa2, that is aes, and tkip algorithms used behind it, along with rsa distribution model, right? So this RSA is nothing, key distribution. What is it? The quantum computers with the with enough capabilities to break the RSA. Can you imagine? We can break RSA now. So the duration was, think about that duration. That duration was something like, you can say, uh, I told you, like 2 into 10 is to power 56 years. And now, if you apply that same algorithm, let's say brute force attack, again only on this particular model of 32-bit RSA, obviously it's compromised, and I think it would take not more than 2 hours or something like that. In case you have a multi-dimensional, like arrays, or you can say within the room, think about within the room all such activities are going on. Let's say I'll give you a small example. Player, let's say badminton, two players are playing badminton, and you are recording. So I deployed in the room, or probably you might have seen today all the video makers and animation movies. You might have seen these new concept in this movie called this one South Indian hero, uh, and various, like in RRR, or before that there was one more movie, Bahubali, if you might have seen. And so a lot of VFX effects you might have seen, right? Avatar you might have seen. So think about the Avatar movies, or Bahubali like movies, or like such animated movies, and we want to replace with any particular object with other objects, and all the motions, all the frames in 300 fps. Think about even more than that, even uh, 1200 fps. Very high. For that you need a very high GPUs, but at least these days movie makers are working with the 300 fps, right? So the frames per second are like almost 300 frames per second. They capture that information, and now they are trying to replace that objects with any animated video, animated, like one tiger is running towards you, right? Although actually one person is running towards you, so they pick that object as a person, as an object, and replace all that person with their motions, with their behavior, their facial expressions. So think about that dimension. They pick that all data and convert it to a object like a tiger. So one tiger is coming towards you, all VFX effects are coming up these days. So it's all because of high graphics model. But this is very small thing which has already been initiated. Although for that also your CPU won't work. You need a high level GPUs, right? Probably you might have heard about like blockchains. Did you heard about blockchain mining? Another example. For blockchain mining, you need a high power consumption is there, because you deployed a big huge GPUs, and that GPUs are going to you can take it like say, if I'll give you example like 128 hexadecimal values, and on that I use a concept called, let's say, hash, and I will say d hash, or I would say salting on those hash values. So certain hashes are there, right? And 5 and 2 bit hash generates 128 letters of hash. SHA 5 and 2. SHA 5 and 2 algorithm generate 128 letters, hexadecimal 128 letters. Now you have 128 letters for one particular value, and probably that value is not a value itself, is a huge data. Probably you can consider like trillions of transactions in one indexed point, right? Where we are applying one, and on that index point we are applying hash value. So generate the hash, and let's say to make it more anonymous and more secure, we apply one algorithm, and that algorithm is like you can use salting on hash. So that is a hash salting model. So if we salted means let us try to find the pattern values, and let us replace those pattern values with applying another algorithm onto it. So you can apply multi-level of algorithms. Now if you have multi-level of algorithms and generating a new data out of it, so how you can decode it, right? So what is a model of decoding? We need cryptographical relevant quantum computing, so that they can able to understand. So for that there's a concept called that's what I said, qubits, right? So those qubits are needed and dependent on it. So it itself working on the collection. Just try and understand. Let's say you have a data per bit. So what is the data? Traditionally, if you have in binaries, you use the value 0000. Suppose 8 zeros, 8 bit zeros is the value. Decimal value is always 0. Okay, so again traditionally, if I take two good bits like 01, 01 would be represented as 1, 10 represented as 2, and 11 represented as 3. So this is binary example, just to correlate with your quantum, right? And now if I have a 1 qubit, if we have one particular qubit, so one qubit, either it is 0 or 1, so automatically it started with two-dimensional model. One qubit started with two-dimensional. It could be 0, it could be 1, both are there. So it means they're starting with the concept of listing, or you can say the array. So finally it goes to the multi-dimensional arrays. Now two qubits means now they have four dimensional, 0 to 3. 3 qubits, again it is like 0 to 8. So any values can be easily adapted by quantum, and they are ready to work on diversification of the data processing, diversification of the multi-dimensional model. So that is how the your quantum actually works across, right? Even if you have a 4 qubits, then 4 qubits means you have a 16 dimensions. Can you imagine? So you have then 16 dimensions. And the classical model, if you read the power used and the classical, like the bits which you are processing, so you can say the classical model, it works like 0 to 8 bits. So processing in the red is basically a classical model. And for quantum, you are talking about 8 qubits. If it is 8 qubits, it goes fractionally the power consumption. You can see how it is rising like anything. So where today still we people are working on bits model, bytes and bits model, and our consumption level is this much. If we deploy the servers, if we deploy the the architecture of any application today wherever we are working, but think about the volume of the data which rise in the qubits, and accordingly how much power is required at the parallel point. If you can see, I think you can say 150 or 130 or 120 points. If I'll talk about this particular point, you can follow my mouse cursor, right? So if I am on this particular point, it means 120 times extra than the classical model, right? I hope you understand what I'm talking all about and why it matters a lot. Like now think about cryptographic, right, or cryptographic breakdowns which we require to find the patterns of the cryptography, and how the hackers are basically trying to decode or decrypt your data. Even you are using certain keys, so pattern matching of the keys, वो आपने देखा ना, you might have seen like uh, you or might be nearby somebody, you might find the person who can create a duplicate keys of your locks. How that person, did you ever try to see those guys, how they people tried, they have some common combination model, so they already have some common combination models. Based on their common combination, they have a pattern of the keys, so they have a collection of keys, and it's a very generic. And the moment they try to apply in their lock, they try to figure out the gaps, they try to figure out the patterns of the keys, and on that basis they try to hit or generate certain level of attacks to those directions, or that particular where you have a spring sort of within the lock, and they try to decode, they try to create a duplicate key. My concern is, can we create a duplicate key of asymmetric cryptography? Because we are using RSA algorithms, we are using various other key distribution models are there, which is again the challenge. So think about, in case if we have a 1000 qubits, can you imagine 1000 dimensional model where I'm talking all about 1000 qubits? So see certain results on certain algorithms like AES. If we'll talk about AES, securing data on hard drives, right? You have a data on your hard drive. Did you ever try to encrypt your data on your hard drives? How you secure your data? Means you generally used to share your data and place your data directly to your Google drives. You have a pics shared on Google Photos, or you have emails, you have attachments, you have confidential data again shared with Google. So Google is giving you all those free services because they are going to access your data. They really want to analyze your data. So that's a concern where the people are working on it, right? I will share one algorithm, one very basic algorithm where you can generate your own key, right? I'll show you small practical in case if you want. I have personally did that. I have a small code, but very small code, which we are trying to work to secure our data. This is how we people are using. We use Google also, but in a little different format. uh, so the best practice, first I will say the best practice is you create your own NAS drives. You take your own data at your home. Make your own Linux server at your home. Very simple. You take any old laptop which you are about to, it's a e-waste for you. Don't generate e-waste. Convert that e-waste into the servers. That's a first best practice you can try. But obviously, it is not computing like quantum computing, but at least you get a process how to apply, right? Then as you have like 4 or 5 members at your home, so let all members have their own unique id user IDs and let them save their data. Or what all the activities we are doing, can we clone or we generate the synchronized data model on one of the centralized device? Now think about same if you can do on your in your college or in your campus. This is a real time project I'm giving you. If any professor into the research, they can apply this. You already have the Wi-Fi campus, probably it's a part of now UGC or AICT, NBA, NAG accreditation, you know it, all these things, AICT, all that, right? So you already have a Wi-Fi campus. Did you ever, the person who deployed, did you ever try to ask them, come on, give me the logs? Which user work on which URL at which time? How much time they spend on on networks. Excuse me. So, how much time the people are applying? Uh, which user is more on internet? Means this is a very simple and small project, but very, very valuable project. Please try and understand. And you can take it with using small machine learning algorithms as well. First, you collect the data. Let us have a realistic data. So, whatever the Wi-Fi service provider or the device which you have used for distributing Wi-Fi's, and you probably have a, just like you have, let's suppose, 5,000, 10,000 user in your campus, and all those campus have the users and whatever the link they are accessing, what time they access their internet, and let's have a kind of a proxy servers they must be having. You must be having, right? So you have a one all the URLs. We are not talking about data breach. We are not talking about privacy breach or something. But what I'm talking about, and even this is what being done by all your telcos, all telecom companies are doing this, take my words, right? So let's say today your campus, your management want to say that let us go and block social media or some objectionable site. I want a list of some objectionable site, and let internet is there but we want to block it. So we need to see which user want to hit on those objectionable site at what time. Let's say we have certain patterns. Can we analyze those patterns? So I'm giving you the live projects. Like, okay, this is a very basic one. But daily you might find if you have 10,000 user and each user is accessing, let's suppose 200 website, 200 links, probably WhatsApp 200 times. Hardly matters. They are just going through WhatsApp and sending message, receiving message and all that. So all the transaction is going on, right? I'm talking about, can we capture those URL? And that URL is again what? URL is a user agent value or a URL. So these are all the certain parameters in the web servers or your proxy servers which you can filter. Based on that, or even you got the IP addresses, even you will get the MAC addresses of those devices. So which device, which MAC address belongs to which particular device, the way how you have to produce the data. So this is again data aggregation model. You need to sometimes produce, or data mining model. You add that data, collect that data, produce that data or relevant information and generate the huge list. I'm telling you, even you can't work out more than 2 to 3 days data. If you have 10,000 users and 10 days for 10,000 users, your system, you won't be able to work on your even laptop. It would take huge traffic and huge data need processing required. So probably you need a good machines so that you can able to process such data. That's what, like in your AI machine learning, we want uh, AI based or GPUs, especially GPUs being used to handle AI or machine learning model, right? I hope you heard about these things, right? So let us say we have a hard drives, and if there is one data center who have a, let's suppose, 200 hard drives with the capacity of 8 TB each. There are a lot of TBs, 16 TB, 32 TBs, which we can apply on server. Let's say 8 TB of 250 gig hard drives, and fully occupied and processing based or database based, where you are inserting, deleting, adding, updating data very frequently, so indexing won't work properly at that point of time. How you can secure that data? By applying the concept like AES, advanced encryption standards, right? So large key size recommended. In that case, the impact is what? The larger key size recommended. Otherwise, you cannot store your data or secure your data. This is again problem statement, or you can say the common issues or common usage which is required. I told about you about SHA2, SHA3. So I have already given you the example of SHA 512, and which generates a 8 keys. And let's say we'll do a dehashing or salting on hashing with certain patterns based, and to identify that patterns where you are making changes in the data packets, and then the hash is different. If you revert that data, then the hash is different. So we'll match those hashes, and then we identify which data belongs to which purpose and which in which particular context. So these are the areas where we used to explore. We are working these practicals, right? That's what I'm saying. RSA challenges. So secure browsing with TLS HTTPS packet. Have you heard about one concept called HTTPS stripping? Anybody heard about HTTPS stripping? Anybody heard about what is HTTPS stripping? So there is a concept called HTTPS stripping. Now, what is HTTPS stripping? If let me see if I can share something. Okay, let me open a paint for you in that case. Uh, okay. In this regard, let me view some see what is this HTTPS stripping all about. The model is like, say, I'm not good in painting, so please excuse me for this. Let's say this is my machine, and this is my one of the router, and let's suppose I connect it to the internet. This is all my internet, right? Today you have HTTP, you have a basically end-to-end encryption with TLS, transport layer security. So that is what transport layer security we are talking all about, and HTTPS and all that, using RSA on the back end, right? So secure browsing is nothing based on TLS, HTTPS, identifying documents, electronic health card, data encryption, integrity checks, security signing, message protocol protections, programmable smart cards, and authentication tokens. So various things comes with this particular part in regard with the RSA. That's what, like, today RSA is more famous. Please take my words, it is no longer secure. You might have seen a few of the videos where the expensive car stolen because they have a RFIDs, they have a special impact. Like even in India also there are some cars where if you just take a key along with you, if you reach to certain place, that car automatically unlocks, right? Or they recognize the key if the key is within the range, so it automatically unlocks once you reach or you touch the handle, let's say NFC or RSA with RFIDs. So these kind of things were already there. So it is generating a lot of data, and that data also connected to internet and goes to the concerned authorities. So IoTs are also generating huge data. Please try and understand. So my concern is, like, today if I am connected with this particular part, this is my machine, I am connected to the router. So this is my router. Okay. So my router is connected to, let's say, website, and this is your internet. Okay, I'm very bad in writing, so please apologize me for this regard. And there you have, suppose, one web server, and let me access my web application. So there you have a HTTPS. Let's suppose this is a banking website like SBI. I'm taking a hypothetical case, right? And they have internal infrastructure where multiple devices are internally connected. Okay, suppose I want to access, I want to do a online banking in this regard. Today, they people have started working with the HTTPS two-factor authentication or multi-factor authentication. But authentication is one part. They have a cryptographic algorithms on this regard where they use TLS, transport layer security. With we are connected, you can see whether we are using HTTPS or not. So this WebEx, they have a connection which is secure. So obviously it is HTTPS. But which HTTPS did you ever try to analyze? Even this is the way how you can analyze the phishing attack as well. So you can see my screen, this WebEx. If we are on WebEx, this is a product of Cisco system, and the HTTPS, this digital certificate issued to them by Trust, one of the organization who must be a CA, right? A certifying authority who delivered the signature, this digital signature or digital certificate to this webex.com, and that must be a wild character digital certificate, right? and that is issued on which date, which time. So you have some artifacts with SHA 256 fingerprints are there with certificate key, and public key is there. You can identify these keys. Now, my concern is, if I'll give you these keys, you have these keys, right? Based on these keys, make a one Python code. Can you create a one Python code where, based on that Python code, you collect these public keys and identify the pattern of the public keys of, let's suppose, uh, at least start with 100 website as a sample project, but let's say we want to consider a 1 lakh websites. And in case if you found similar pattern, this similar pattern might be belongs to this digital certifying authority. So probably you might have some common letters, initial letters in this 256 bit encryptions, right? So 256 mean these all are 64 letters. Please take my word. These all are hexadecimal 64 letters. So you can consider this complete 64 letters, pick these 64 letters, or the level of certificate where you can we identify the patterns in this regard, which simply describe that this these certificate being issued by Ident Trust organization. First case. Second case, let's go and get into the detail, and let us try to identify their versions. So version 3 itself is TLS based. So I told you, in this we have a TLS HTTPS secure browsing. This is what presently going on. So what is this? I'll show you. Version 3 is there, which is TLS based. Okay, so you have a serial number, you have a certifying algorithm. Which algorithm? You can see with RSA encryption. Technically, you can see this is RSA encryption. Please take my word, this is no longer secure. Why this is no longer secure? I'm sharing that what practical to one concept to you. At least you need to understand the concept on this regard, and how it is simply being hacked by cryptographic quantum algorithms, not by regular cryptographic algorithms or regular hardware impact. So we need a hybrid technology. We need quantum, and we need the common algorithms at least to be deployed, so that we get a faster process and to get the good results on that basis. So there you have a certificate signature algorithm, issuer you can find, and all that fine things are there. You can find the validity, that's okay. Public key, what are the public keys? RSA encryption. And see, you can take a look. RSA 3 generally use 2k bit, 2k algorithm. Now this is 2k. Now if you have that 2k model, can I pick that 2k model? I just gave you hash value. You first try with a hash. Okay, now you have a 2k model. Based on that 2k model, okay, can you decrypt or at least identify some common patterns from this particular public key? This is again a kind of a public key generated on the public exponent 17 bits which are there, and they might have shared a 2k bit data. And if I apply any brute force or dictionary attack on by using 1000 qubits, if I applied on a quantum, then 1000 qubits are going to help me on this regard. They will solve my problem on this regard. 1000 qubits are going to work out, right? And on that basis, if we will go and find or figure out the data, you might have seen it is also based on TLS model. You can see the TLS identified. What is TLS? So it's a server and client level authentication. That means they are talking about end-to-end encryption standards. Understood? They are working on end-to-end encryption standard. My concern is, can we hack this end-to-end encryption standards? Is it possible? Yes, it is possible. How come it is possible? So for that, you need to understand this model all about. Let's suppose I have this model now. Today, in your organization, if I deploy, or today people are these days, you might have seen using VPNs and all. So today your systems are directly connected to router, and routers are connected to internet and doing all this internet banking. No, what my concern is, let me deploy one particular, you can say, proxy server within the network. So all my Wi-Fi users, so let's say I'll assume lots of Wi-Fi users are coming across to your access point. This is your Wi-Fi access point. Let us completely, I'll make it, let me take a bigger one, something. So this is like access point, right? Let's suppose this is an access point, and now you have hundreds of users working at that time. Okay, at the same time you have hundreds of users who are working in a particular regard. So I'll just increase the brush size. So there is a one machine, second machine. Okay, so you have a Wi-Fi in your campus. This is what the example I was giving you also, right? So you have a Wi-Fi in the campus, you have multiple machines, say 5,000 students along with faculties, or 10,000 people are there, or 5,000 people are there who are going to access your common Wi-Fi interface, where you obviously have multiple Wi-Fi devices. Or you go to any five-star hotels. Recently we are the lead auditors, and vulnerability assessment we did for ITC, ITC Moria, Dhola Kuan, and various ITC hotels, five-star hotels. They deployed 3,000 Wi-Fi access points in their one campus. So all the public users are going to visit that place with their common username and password. They can access their internet services from any 3,000 devices. But these devices are working very near to them only, with very shorter in range but high in speed. So that kind of devices we have deployed, and based on that, the user going to connect with these devices. But these devices are centrally connected with one of the system called Nomadics, one of the server where we are working, and the people are working more on it. It's like a proxy. You just take it like an internal proxy server. Now this proxy server used to generate the records, the logs basically based on their IP, their MAC address. So various parameters are there: IP, MAC address. Then we have their URLs, their user agents, their browsers, their applications, whatever they are using. Obviously, because it is end-to-end encryption, so we cannot hack, we cannot do man in the middle attack. And this case doesn't mean we are doing man in the middle. This is one MITM attack. We can't do MITM. We can only generate logs, and that is mandatory for forensics as well. Because if any user did any mischief activities, or any mischief monga is there in between trying to make any certain attack, so how you can identify that person? ISPs are doing same thing. This is there, you will find the ISPs are doing the same thing, right? The log, your organizations are doing the same thing. They're capturing such information. So such information being generated, and now a complete data on the network, complete data is secure till the time that data reach to their HTTP, their even database on the backend. Probably they must have some DB, or they have some file storage servers and all, right? So file storage servers, suppose we have this DB or file storage servers on the SBI side. Okay, my concern is, unless and until the data is either at this place, so I'll take another color now, either my data at this location, either my data at a particular user location. This is end-to-end encryption. Right? And even in the database, even in this database, this is again encrypted. Okay, this is also encrypted. So there you also have encrypted data. You cannot access the data from this particular regard. So data is accessible only on the source, on the destination, where they are doing a handshake between two devices. That is what session being generated, HTTPS, RSA, TLS algorithms are working, and your end-to-end encryption standards are working. Now, how it is being decoded? Today, people are deploying like proxy servers, right? Or suppose you people are using VPNs. Now, suppose if you use another model like VPN, I'm taking especially red color for VPN and all. You people you think that VPN is secure? Please don't use. That's a false positive result generated by Google. Never use VPNs. I'll show you. Even you go to Google, if I'll write top 10 VPN, please take my word, this is really dangerous. You never know how are these VPN providers. Probably between you, me, or any one of your student who launched this product and deployed on cloud servers. And even if I'll go and access particular site somehow, let's suppose I'll go and access any particular site. You must have seen various sites. Okay, Express VPN. I'll show you some one of the site of it. I'm not promoting. I never recommend people to use the VPN because you are still never aware what is VPN. So if you use these VPN which are according to these sites, please see this all are false positive. You need to see the back end of these sites, right? See how they according to you, you got protected by from hackers, government, or internet service providers, and your system that directly tunneled and being only dedicated and connected via internet and transferred to the data to the concerned authorities. So it means your data, if you have any particular data, let's say this is my color of the data started from this all channel, and finally it reached to in this particular regard. This is how my tunnel is all about. This is what we feel, which is end-to-end encryption. But the people who use VPN, now think how VPN works. They basically, I'm specially taking red color for them. Now suppose you deployed a VPN, so your data goes from the internet. First your data goes to VPN servers. So end-to-end encryption is between what? Now your end-to-end encryption is between your machine to VPN machine. All right. Now your end-to-end encryption is between you and your VPN machine. And on your behalf, the data get decrypted at this location. And on your behalf, the data being generated and transferred via this channel to your DB. And now you have a SSL encryption, end-to-end encryption between the target is SBI server and your VPN. So there you have a TLS. There you have TLS, right? And there you have TLS. Earlier your TLS was directly connected. So please never use these Google VPN. These all are promotional activities. Never accept that. Even see, they are saying we have 256 AES. They are talking about all devices possible, secure connection of 105 countries. Come on, 105 IP addresses of different countries. That means geolocation issues. Now suppose your data goes from your machine to Palestine, Pakistan, Israel, Bangladesh, China, or any damn country, any other country. So your data goes and exposed over there. They decode your data, and after decoding their data, they redirect your data via internet to the target servers. And you are passing your credentials to them as well. And you never know, even you are paying, you never know who are these VPN providers, even they are registered in India or not. So big challenge like this, or this concept is nothing technically, this concept called as HTTPS stripping. Don't get into the concept of HTTPS stripping. These people are going to hack your data, your credentials, and later you might face financial frauds or various other frauds, and you become the victim of such kind of things. Obviously it is not easy to process the huge public data and global server. For that, again, you need high computing. So either you use GPUs, or let's say we'll consider the pool of GPUs or multi-dimensional arrays, so qubits based on the huge collection of GPUs become one quantum, and it is being architecturally deployed in the form of quantum. And finally you got a qubits, and these qubits are working on these grounds. So please take my words, whatever you are doing, why it is not secure, no longer secure. I think now you understood the based on this case study, what are the real challenges, what are digital signatures, how it works, two-factor authentication, or even digital signature based on RSA, or even your asymmetric cryptography. You have private public key model. right? DSA, digital signatures, signature certificates, etc. So please take my words. This is really, really dangerous, and that's the the legacy of security is now being compromised due to cryptography, quantum computing. So we are into security and we deal in these kind of things, and now we are using quantum computing to analyze what are the impacts and how much complex we required and at what level it is required, so that even quantum computing will take time to process, so that we can say somehow up to certain stage. Obviously every technology have the limitation. You cannot exceed. You need that level of funding. You need a lot of manpower, resources, and the ideology, basically the algorithms, basically the technology also on that basis, so that you can generate the results on that. Although threats by cryptographically relevant quantum computers is more than 5 years nowadays, easily publicly available on cloud servers, so you can start working on it. Data captured today can be unlocked by tomorrow very soon. So that's what every organization has already started capturing your data, or at least they started working on your artifacts, right? Their metadata. So they people are working more onto it. They are encrypting that data, and they are working harvesting your data and trying to decrypt using quantums. So I hope you understand what is the issue. So major issue with cybersecurity, quantum. You can understand the impact of encryption, data analysis, threat detection model we use for in this particular part, right? Even though that is a quantum encryption algorithm. Can you take a look? I quickly show you one of the algorithms. So say quantum quantum encryption algorithm. Just simply go and check this algorithm. You can understand the model. See, I have just specially open it for you on Google, so that you can read what is this all about and how quantum mechanics, photons, security, and pioneers in the NIST, they are working like top three post quantum encryption algorithms. So QEA is a one of the project required. This algorithm is required these days, especially for the communication. So Ministry of Telecom started one project recently in the month of October, November. They were open for the bids. One of the organization, we filed the bid on that basis, and they are basically more using for the algorithm for confidentiality and the integrity of the transmission information while protecting against the eavesdroppings. So this is how you can figure out how this QEA works all together, and you can explore. And I think on your research, I gave you a lot of data. I believe you can understand. I have given you a lot of practical projects as like whatever is possible in case of quantum, because obviously I cannot show you the quantum part right away due to some NDA. Even I in the morning I called to the organization that can I show some practical. So they said, "Sir, abhi kaam to hone do thoda sa." So I said that's okay, but I gave you a real concept. What is the real concept of this altogether, and how we people are working on it? Breaking traditional encryption. I have already explained you how it breaks actually traditional security and backward compatibility, increasing attack sophistication. So many things are started, and you can explore one by one. This is quantum key distribution, QKD model for security communication. So I told you in a quantum encryption algorithms, nothing but the key distribution model. So we are going to work on these key distribution models a lot on it. So a lot of opportunities comes with the quantum computing to bring in terms of cybersecurity for threat detection. How can you do threat detection if you have, let's say, 10,000 students or users in your organization, and those 10,000 users can access, suppose your email servers or web servers or something like that, and there any one user is doing any some illegal activity, or I would say some eavesdropping in the networks, or making some challenges, and it's very frequently daily you might see seen or notice these kind of things. but you have a very less data. Probably you can do it on computers or GPUs or CPUs. How to think about, if I get the data of last 5 years of 5,000, 10,000 users and the processing, again GPUs are required, even that won't be able to handle it. Then in other way, finally we have to go to the high performance model. For that we need a quantum algorithm. So start working on quantum algorithm. For that, let's stop using key distribution of asymmetric cryptographic or existing algorithms, or very legacy based algorithms like RSA, AES and all. Let's think about QEA algorithms or quantum key distribution models for secure communication. So today government has already initiated, government of India has already initiated, can you imagine? So please think about it and start working. You need to explore a lot on it, then you realize what the content all about. I quickly try to show you some basic thing. I think you have seen quantum experiments Google is doing, IBM is doing, in NASA, NSA quantum safe initiatives are there. Some case studies you can identify. And high cost deployment and development is there. Obviously, these are the challenges: interoperability issues, skill gap problem, regulatory and legal issues are itself is a challenge, right? So future directions, yes, start adopting the post quantum cryptography. I told you about PQC, that is post quantum cryptographic algorithms are there. So let's think about another level, next level research part in quantum and collaborative research with industry. So we are open to establish the center of excellence with your organizations terms of cybersecurity, quantum computing. If you people are interested, you can connect me personally, and we can help you in deployment of certain labs, and we can even give you some good projects on that basis, right? So we have some projects where we have some sample research projects we have initiated. We'll give you that level of data. Means if you're really looking for the data, we have the, we can give you at least the sample data, but sample data means you need TBs of drives, right? That is my sample of data. So we can give you that level of data so that we can at least start processing with GPUs. And obviously you're stuck on GPUs, then you realize we need quantums, we need qubits, right? So I think time is less, and I almost wind up, and I exhausted your time. uh, well, thank you so much for giving me you're the patient listening, and you're interacting and you're still listening after exhausting the whole day. You people might be exhausted and spending the whole day, but thank you so much. Thank you. And over to the organization people for giving me the opportunity. Hope you enjoyed. I'm open for the question answers in case if some questions are there,
Thank you so much, sir.
sir.
Sir, thank you so much for such an insightful and thought-provoking session. Your expertise has undoubtedly expanded our understanding of how quantum machine can play a pivot role in cybersecurity. Participants, we
Sir.
hope you find the session enlightening. Please remember to fill out the feedback which is available in the chat box. Thank you so much, sir.
Dr. Bhavan sir,
Yes, sir.
I think there are some queries in the chat session.
Okay, sir. I
Kindly
will.
resolve that,
Okay.
please.
I think from
H.
bottom to top, let me see. Also, some chats
Needed
are there.
Khadija.
Thank you for your valuable feedbacks. I think a lot of good feedbacks are there from various participants. Sir, can we say that project? Okay, what is
Deploying
this?
authenticated
I can't
servers are
read
secure.
actually. New message. Something new message. Okay, let me read now new messages from the bottom. Yeah, sir, can we say that project deployment is in authenticated servers are secure? Miss Joshi, yes, Mr. Joshi, uh, please try and understand. deployment of authentication. First, we need to understand the algorithms of authentication. We have various authentication models these days. We are talking about like two-factor, multi-factor authentication. We have biometrics. You are already deploying your data, even your employee data, your attendance systems are there, but that is very, very, very basic part. Probably that data comes into the Excel form. So authentication security itself, I recommend obviously first that should be in your servers and to be deployed, that is bared servers we used to call it, should be at your campus itself. First thing. Second, the algorithms. Third, the networking process. Fourth, the algorithms for data, TLS and end-to-end encryptions. So there are various factors if you really talk about only for the authentication models, and then performance and all. Right? These are the matters. So it depends, like if what type of architecture you have, how many users you have, how many data, how much data traffic you have. Accordingly, we need to decide. See, cloud is good to go, no doubt in it. Again, it is secure if you use a good algorithms. So cloud is also secure. I'm not denying into it. Initially, if you want to test, you can take it a test directly on cloud, because then you have less expense, less capital need to be deployed, and at least you get some results. But finally, if you have the plan for 3 years, 5 years down the line, then take my words, cloud is the most expensive model for you. Finally, you have to take an initiative that whether you want to deploy a capital right now for big project where the duration of the project, or you want a retention period of your data to be more or less, and you want to really implement that part. Let's say one researcher who start their research, or the community who are into that research, they want that data, then cloud won't be good to go. Then that's what, like most of the organizations, they started deploying their data center in their own organization, so that we can able to process that data due to latency periods, and the retention of the data. So various such certain parameters are there where we have to think about, and then only we have to decide whether we should go with the cloud, or finally we should deploy the servers in house. Right? So depending upon those parameters, we need to take the decisions. But finally, it is always good to go if you have, if you can, means because budget is one of the big issue. But if you can really manage that one, then I recommend keep your servers in your campus, so that you have the complete hold of that data. Otherwise, some third party mediocres are there that might be, they will access your data, or you might get compromised. Many cases came across already. We are today working on cloud forensics. So we got the projects for cloud forensics because people are using cloud, right? And now they are facing challenges, and they are actually becoming the victim of financial frauds, identity frauds, data phishing attacks, and various other types of attacks which are coming across. So we are there to solve those problems, and we are working on cloud forensics architecture. So how to contact? Yes, sure, Mr. Verma, Jatin Verma, sir. Please note down. I will share. I would love to share my contact details to all of you. Even I think it must be on the slide, first slide. Yeah, I think you can see my screen, right? My number is, you can down, or my email ID is 98115729. My new capacity. So you can contact us anytime. It's there. Otherwise, I'll share this PPT, I think, to the authorities, and probably you will get the PPT there also. You can get that. I'll write down on the chat in case if I can. Yes, I can. 9811485729. This is my contact number. You can connect me anytime on this regard, or any particular project, or any area of research if you are working, would be great. Great explanation. Thank you, Mr. Jatin Verma. Thank you, Gajanan ji. Thank you so much, Rohit ji. Various people. Shivani ji, thank you. Yeah, it's fine now. Thank you, Mr. Kumar, Saurav Kumar. I think they must be having some other also issues. Now it's okay, sir. Okay, so might be some connectivity at your end, back end, probably. So I think that thanks goes to the team of RKJ IT, right? Because they might be working on the back end. So that thanks goes to them as well, I believe. Very good evening. So thank you so much. Thank you, Bablu Kumarji. Thank you for giving your great feedback and valuable support. Thank you. Over to you, sir, and the team. In case if we have any other query, they want to interact, I'm here. Otherwise,
Thank you so much, sir.
Thank you, sir. Thank you so much.
thank you, Amitji. Thank you, Dr. Pawan. Thank you, Dr.
Thank you,
Amit.
sir.
Great interaction with all of you. Thank you all. Bye bye. Take care.
Good evening, everyone. Now our second speaker is also joined the meeting. Good evening, everyone. Our next session is titled Basics of Quantum Computing for High Performance Computing Professionals. This session will focus on the foundational aspects of quantum computing, tailored specifically for professionals in high performance computing. It aims to highlight how quantum computing principles can complement and enhance the high performance computing ecosystem. Our esteemed speaker for this session is Dr. Seema Malik, an associate professor at Vivekanand Institute of Professional Studies, New Delhi. Dr. Seema Malik is highly experienced academic and researcher in the field of electronics and communication engineering with a strong background in wireless sensor network. Her educational qualifications include a polytechnic diploma from the Haryana State Board of Technical Education, a BE in electronics and communication from MD University Haryana, MTech degrees in both electronics and communication engineering and computer science and engineering from D. Crust University and NILM University Haryana, respectively. A PhD in electronics and communication engineering from SRM University Delhi NCR Sonipat. With around 15 years of experience in research, teaching, and administration, Dr. Malik is currently affiliated with WIPS Technical College, Delhi. She has further enhanced her expertise, being certified as an AICT Master Trainer in high performance computing. Her research interests are centered on wireless sensor networks, and she has contributed significantly to the field through multiple research papers and book chapters. Dr. Malik is actively involved in the academic community, organizing and participating in conferences and workshops. Additionally, she serves as a reviewer for various SCI journals related to her research area and is a life member of ISTE New Delhi. In this session, Dr. Malik will guide us through the basics of quantum computing, its relevance to high performance computing, and how professionals in the field can begin to adopt quantum approaches in their work. We are in for a thought-provoking and practical discussion. Before we begin, a friendly reminder to everyone. If you have any questions, feel free to type them in the chat box. Without further ado, let us warmly welcome Dr. Seema Malik to take us through this enlightening session. Over to you, Dr. Malik.
Thank you, Pawan sir. Thank you very much for the great introduction. Am I audible to you all?
Yes, ma'am.
Okay, thank you. Thank you very much, sir. So should I share my screen?
Madam, yes, ma'am, yes.
Okay. Okay. Let us start with this topic. The topic for today's session is basics of quantum computing for high performance computing. So basically, today's talk outline is on the basis of HPS introduction. It's HPC means high performance computing. which will be going to relate with the quantum computing, because HPC and quantum computing both are extremely related with each other. So first we'll go with the HPC introduction, then we'll move with basics of HPC, then we'll go for architecture of supercomputing system, then parallelization paradigms, then intersection of HPC and quantum computing, then why we need quantum computing basically, especially for HPC professionals. Now, how to build quantum expertise for HPC professionals. Then we'll go for applications, then challenges, and then finally future outlook and summary. So this is my talk outline for today's session. So first we'll move towards introduction. So on your screen, you can see a computer, the first computer. The name of this computer is ENIAC, which was introduced to us in 1947. Here you can see lot of wires, lot of racks. In today's scenario, this type of scene is available for supercomputers, but at that time, this is for ENIAC. This is for a computer, for a single computer. Right now, which we have a single computer in our laptop only, but at that time we have this computer in a room. The reason behind this is the transistor size. So hope you might aware about the three terminals of your transistor, that is emitter, source and collector. So the gap between the source and collector is known as channel length. So the channel length is very large during 1947 for a transistor, and this is the only reason behind a chip, that chip size is extremely large. So because of this chip size, the size of the motherboard or size of the other circuits are extremely large. That is why the system is within a room. Now, this is the basically transistor evolution. You can see in my screen there are two colors. One is green line graph, another one is blue line graph. So the green line graph shows that till here we don't have transistor evolution in a perfect way. But when we start with blue line, it shows that it is around 1956. We have transistor evolution as fast pace, because the channel length, which is between the source and the emitter, is going to reduce day by day. Why it is going to reduce? When transistor size is going to reduce, the chip size is going to reduce. You can relate this to your past, maybe to your past experience with your pen drives, with your hard disk. You have big size for that, but right now the size for your pen drive, the size for your hard disk is extremely small rather than previous. Next, how we can measure the power of a supercomputer. So supercomputer power is measured in unit of floating point, that is floating point operations per second, that is used to measure the performance of a supercomputer. So here we have some values. You can measure teraflops, you can measure petaflops, exaflops, zetaflops, yottaflops. So these are basically the power, how we measure the power of supercomputer. So here are some examples of high performance computing which we gonna use in science. So first we'll take example of atmospheric science. So in case of atmospheric science, you will use high performance computing to measure the climate or to predict the climate or weather forecasting. So you can also use this for air quality monitoring. Now, another is you can use this high performance computing for earth science. So applications which we gonna understand in physical properties, in geological structure basically, that is used by high performance computing only. So next we have space science. In case of space science, we also use our high performance computing. Another examples are, you can use life science. In life science, you can take example of drug designing, then genome sequencing. A perfect example for this life science is your corona disease. You can relate with corona science disease. So when we have corona COVID-19, during that pandemic, will have I think within week we will have the drug for the COVID. So this is because of this high performance computing only. Then we'll use this high performance computing in nuclear science also, in nanoscience also. Then if I'll talk about its applications in engineering field, then we can We can choose crash simulation, so which we gonna use in automobile and mechanical engineering. Next, we'll go for aerodynamic simulation, then structural analysis. These are examples in case of engineering, high performance computing applications in engineering basically. So we'll take one more example, that is weather forecasting. uh, we have throughout India we have various area space with us, and at any moment we have weather forecast in our mobile at any time. This is possible only because of high performance computing. So we'll move towards basic of HPC. So this is the book which we use for high performance computing, because recently, if I'm talking about North India, then this is not that much popular, but in South India it's obviously popular subject and used by our final year students basically. So parallel computing book for this is this Almasi. Then according to this, a large collection of processing elements that can communicate and cooperate to solve large problems fast. So this is parallel computing. So high performance computing and parallel computing both are related to each other. Because of parallel computing only we can achieve high performance. So this is evolution of HPC, that how we moving towards high performance computing. Initially we'll have one CPU and one memory. Here one CPU means one core. So core means you can say a ALU and a memory. A set of memory and ALU is known as a CPU. So one ALU can perform one operation at one time, and that performance will be saved into a memory. So we have one memory and one CPU. Then after some time we'll have two CPUs or two cores attached with the same memory. That is known as shared memory concept. Then after some time we have another one concept with us, that is we have various cores or various CPU inside a CPU, or you can say various cores inside a CPU, and every core have their different memory. So in this case we'll use various type of architectures. We must need to know address width, we must need to know data width, we must need to know number of cores. So what is the clock rate, what is the period, everything data we have over here. So next one is execution of thread, block and grid. First I'd like to know what is thread. So as I told you that we have various cores with us. So one core can process a single task at a time. So here process is nothing, it's a thread only. So when we call a process or you call a thread, both are same thing. So one core process one thread. And or you can say if we have various threads with us, that is known as block. We have a block of threads, actually 32 threads inside remain inside a block, 32 threads basically. So thread block will executed by the streaming microprocessor multiprocessor, which have various multiple cores basically. So then we have grid with us. Grid is again combination of thread blocks. Then we have GPU units with us. Right now, a previous speaker told us about GPU. That is graphic processing unit. Graphic processing unit. In previous time, we have separate cards for graphics, which generally use for playing games. We generally use for some animation or such type of games. So in that case, here if I'm talking about GPU, then it is for the high demand of memory, or for the accelerating speed, because we have to work on big data. Basically high performance computer is used for execution of tasks with extreme high speed. Then we have parallel computing basics with us. First we have as I told you, parallel computing is extremely related with high performance computing, because without parallel computing, it's not possible to get high performance. So principle behind this is large problems which we can often divide it into smaller ones, which are then solved side by side concurrently. So next we have parallel processing with us. We have a task, solving task by making simultaneous use of multiple processing elements. Here multiple processing elements means cores. We have various numbers of cores with us, and every core works side by side simultaneously basically. So distributed computing means, yeah, is there someone? Yeah. So distributed computing means solving a task by simultaneous use of multiple processing elements which are isolated and heterogeneous in nature basically. So this is perfect example of parallelism. Here you can see a car, a racing car, and a lot of people working on it during racing period. Because of this only, I think few milliseconds it will take to change the tire. This is the power of parallelism. So this is the basic system architecture behind high performance computing. Initially, we have a single core processor, we have a single core and a single memory attached to it. Then our microprocessor changed to multi-core processor or core to duo, and recently we have Intel 1, 2, 3 to 7. I think right now work going on i9 now. So in multi-core processor, we have more than one core inside a single CPU, and that will share a single memory. That is multi-core processor. Now, what is high performance computing? Basically, in high performance computing, we'll use parallel processing codes. Parallel processing codes. What are these parallel processing codes? Basically, we'll divide our code into various modules, and all these modules are independent to each other. So here we have various computing technologies with us, which are very fast numeric simulation, modeling, and data processing. So we'll use computer power to execute a few application extremely fast. So here you can say a supercomputer is a system that performs at or near the currently highest operational rate of computers. So next we'll moving towards architecturing of a supercomputing system. So here we have the architecture of supercomputer, or here we call it basically a cluster. So first we have some networking gateways with us. We have login nodes with us. We have boot servers with us. Management nodes with us. Compute nodes will go one by one. So let us start with login nodes. See, as I told you, we have various cores with us. So some cores, some combination of core is known as node. So core depending upon our structure, basically we'll move towards approx 82 to 86 core in a node. So some node assigned to login nodes. Now why we need to assign these as login nodes? The reason behind this is the user which need this high performance facility for their personal task. In that case, the user needs to have login and password, and using this login and password, user can access the system, this high performance computing, generally used for PhD task. Suppose someone PhD scholar work with high with the big data, which have a huge amount of data, and it's not easy to execute with a normal laptop. So in that case, you need a username and password uh, from this high performance computing facility, and through this login you can work with it. So all these login nodes are having the record of this type of users, and which user needs how much CPUs and how much GPUs. It is also depending upon the user's need. So next we have boot servers and management nodes with us. So here boot servers, as in our laptop or in our desktop, we have booting process with us. So booting process is same here, but will reside in boot servers. So we have management nodes. Management nodes also handle the CPUs and GPUs. So suppose one user need 10 CPUs and two GPUs, then it maybe that GPU space still left, then that remaining space provided to some other user, that will manage by management nodes only. We have network gateways and local network, that is obviously for the internet connection. Then we have switch fabric. I'll show you later about this switch fabric. Right now you just understand we have nodes with us, and these nodes are reside inside the switch fabric. We have compute nodes with us, and we have accelerated compute nodes with us. Compute nodes is your CPUs basically, that will perform your task but not as that much speed as GPUs. So we have another type of category also with us, that is accelerated compute nodes. So these are better. These nodes have better speed than your normal compute nodes. So depending upon your need, what facility you want, you CPU want, you want accelerated CPUs or you want GPUs. Next, you have storage acceleration. Again, we need memory here, so this is a part of memory. So you have backup servers over here, parallel file system. All these are just to keep your data safe. So this is all about the components for your supercomputer. Next, we have a cluster. So cluster is nothing; it's a group of nodes. So as I told you in previous diagram, see, we have login nodes and we have another node. So we'll categorize these two over here. We have various nodes with us, which for basically over here in this diagram we set two nodes for login nodes. You may increase or decrease it as per your need and size of your cluster. So here remaining we have compute nodes with us. These compute nodes may be more than 86, but generally it remain 82 to 86. So various connects between them. So one node have various nodes. I'll show you. Sorry, one node have various cores. I'll show you. See, here we have one high performance computing cluster. Inside this we have a single node. One node have two sockets. Each socket have various cores. So as I told you, one core means one ALU with a memory. So here we have various cores and various memories. So now there is one question with us: how you'll utilize all the cores efficiently? So because this is again a big question mark. Suppose out of 86 cores, 10 cores are not working. So how will manage the load between the CPUs and between the GPUs? So this is a concept of basically shared memory programming model. So how we'll utilize? For this, we'll use one software named as OpenMP. That is Open Multiprocessing. This is a software which is available on internet, that is open source software basically. Through this software we can utilize all the cores effectively. Basically, what is OpenMP? OpenMP distribute the task between all the CPUs and all the cores properly. So here you can take one more example. Over here we have parallel programming two models. One is OpenMP, another one is MPI. OpenMP is based on shared memory model. Here we have various CPUs attached with cache separately and then sharing a single memory. All CPUs share a single memory. Basically, OpenMP is used within a node. As I told you, that a node is combination of various cores. So when one core wants to connect to another core within a single node, in that case we use OpenMP. And if I'll talk about MPI, that is message passing interface, that is again a open source software. This is for distributed memory model. Here you can see a single network and different CPUs, and every CPU have their own memory. So this is MPI basically used, if I'm talking about in a layman language. So MPI is used basically when a node, here I'm not talking about core. In case of OpenMP, I'm talking about a core basically, that when within a node a core wants to communicate with another core. But here in case of MPI, one core from a node is want to communicate with another core which remains inside another node. In that case we'll use message passing interface. Hope you understand this. So here we have HPC software stack. See, if I'm talking about high performance computing or supercomputer, in that case, it is somewhere different from our normal PCs or somewhere different from our laptops. In that case, we can't go for Windows because that is not secure. So it's mandatory for a supercomputer that we have to go for Linux based system only. So, if I'm talking about middleware application and management, so as you all know, Linux is totally based on command system. So here we'll work with commands only. So whenever here you can see in middleware application system from the lowermost we have cluster monitoring software, that is Ganglia, Nagios, and XD mode. Cluster monitoring means it is just to manage the load between various cores. So Ganglia is designed by CDAC Pune only. Same Nagios we have and XD mode we have. But out of these three, Ganglia is designed by CDAC Pune by their own. So next we have the common system. You can say it's file system. Then you have its job scheduling Slurm. This is important again. Slurm. Slurm is your job scheduling resource management software basically. What is Slurm? Slurm assign you the CPUs, assign you the GPUs as per your need, whatever you want. But obviously, because recently all supercomputers available in South only, I don't think in, I think DU still trying to purchase one high performance computing facility, but till now it is not available. All facilities available in CDAC Pune. You may heard about Param supercomputer. You may that is available in 1989. Then we have various updated versions with Param. Then we have Param CD. We have Param Vidhi. We have various recently Modi ji inaugurated Rudraksh. That is again a supercomputer. So Slurm is used for job scheduling. Job scheduling process means whatever the task you provide to the supercomputer to get result basically. That Slurm is used to schedule your job. So high programming tools, here you have sorry, HPC programming tools. Here you have various monitoring tools with us. In monitoring we'll see which one CPU or GPU is not in use right now and which one is in use. All these facility provided by these softwares. So various components of supercomputers which we have seen, another out of these, one is processor, then memory, then interconnects. Then we have various accelerators, coprocessors, storage system as like normal PCs, like all these system. But here we have combination of these, not a single unit. So here is the picture. As I show in first slide that we have a PC named as Inayak. That is a single PC over there. A single which right now which is available in your laptop. But here this picture is for supercomputer. Every rack have one CPU, and each CPU have their own capacity. Okay, so here you can take this is a single rack, and inside this rack you have this CPU basically, CPU, or you can say a core. Okay, so this core will remain inside these boxes. So generally we create a supercomputer inside a room, which you can see in this picture, inside a room. And in this room we have various racks, and each rack have various cores. And we at back end we have its wiring also. And this facility need a extreme chilled environment. That is why the reason behind this is that we have ACs even its bottom part, just underground the floor. So this is dual socket motherboard. You can see here, this is our socket. So we have dual socket part over here. Why I'm showing this to you, just to give you a detail about why we call it dual socket motherboard. Dual socket means we have multi-core CPU over there. So you can see we have core 1, core 2. So each core attached with its cache just related to bus interface and caches. Then we attach with the external bus basically. So here each unit is called a core, which read and execute program instructions independently. So this is inside this chip. That is why I show you the previous diagram over here. All these facility, the multiple cores. attached with this chip only. That is why it is called multi-core CPU. So next we have dual socket motherboard in a node. Now this is advanced version. See, we have single core, then multi-core, core to duo, and then updated version. So how these versions are updated? So we have core 1, core 2, and a single bus interface. Then again we have another core, another core 2, the same set, and both these sets are attached with the external bus. In that case, we'll go with dual sockets motherboard now. If a motherboard have a single socket, so obviously its power, its capacity remains half. But if you make it double, then obviously capacity also doubles. So there are various advantages of parallel computing. So one is the obviously we have actually not the limitation exactly. If I'm talking about the advantage, so calculations becomes easy. That calculations which may take days, weeks, or maybe years. See, if supercomputer is not with us, then in that case we never we never discover the drug of the COVID-19. Because of this high performance computing and its speed, the researchers or the scientists read the genomes of the COVID-19 peoples, and according to that research, they gave us drug according to the genomes study of these peoples. So here we have more CPUs that can get job done faster basically. So that will save our time, solve bigger problem in few minutes or within few days. Then there are some use of high performance computing. So here a team basically assigned to for this task, or you can say team of domain experts and computational experts to develop this application. So and for this team, the developing high performance team, basically that is for designing parallel algorithms, writing parallel codes, or making use of parallel programming frameworks. So open source, here we have various applications open source, as I told you, MPI and OpenMP. These two are sources for this. So parallelization paradigms. See, as I told you, we have one domain here. This is one domain. We have one. This is a program basically, and we divide this program into various modules. So we can see various modules over here, and all these modules are independent to each other. They can run separately by different cores, and we can collect that data accordingly in a single thread. I'll show you through another slides also. So what in ideal situation, we have each processor, we have various processor with us. Processor means a core or a thread. So we have a processor with us, and each processor has a unique work to do basically over here. And communication among processor is largely unnecessary, okay, because everyone is doing their own work, so we don't need any communication. So all process do equal work basically. So for parallel programming, we need to apply some parallel algorithms. So you all aware about these algorithms, I think. Just go through it. One is phase parallel algorithm. Just to all these algorithms are just to make our task parallel, independent to each other. So for this we have phase parallel algorithm. Then we have divide and conquer algorithm. Then pipeline and the process form. So in phase parallel model, just go through it very sharp. So in phase parallel model, we have basically a parallel program consists of a number of super steps, and each has two phases. One is computational phase, another one is the interaction phase. In computation phase, we have multiple processes, each perform an independent computation, and in interaction phase, the processes perform one or more synchronous interaction operations. You can take example of a barrier, or you can take example of a blocking communication over here. Next is your divide and conquer model. It is just like our college structure, that we have one director with us, then inside director we have various HODs, and inside various HODs we have various teachers with us. Then whenever teacher do any task, they will provide it to HOD consolidate that task and provide it to director. So this is same type of model, divide and conquer model, where a parent process divides its workload into several smaller pieces and assign them to a number of child processes. So this paradigm is very natural for computational tasks basically. So next one is our pipeline model. Here we have our one data stream with us, just like a pipeline. So we have a pipeline over here. The in pipeline paradigm, we have a number of processes for virtual. Basically, this is a virtual pipeline, and over here we have data stream, which is fed into the pipeline basically, and then processes execute at different pipeline stages simultaneously. So next one is our process form model. Over here we have one master, another one is worker. He again you can take example over here is again for our organization, that a leader give work to the teachers, and then teacher complete their task and given it to master. But when master sees that this worker is very efficient and doing this task is very efficiently, then master again assign another task to same worker. So this is known as a master worker paradigm. A master process basically execute the essentially subsequent basically sequential part of your parallel program. So whenever a worker finishes its workload, it informs the master, which assign a new workload to the slave. So here are some desirable contributes for the parallel algorithms. So we have concurrency over here, we have scalability over here, we have data locality over here, and modularity over here. So concurrency means the ability to perform many actions basically in one time, because we have various cores and every core doing their task separately. In case of scalability, then here we can increase the processor count or we can decrease the processor count as per the scalability of our supercomputer. So data locality means if various cores, if I'm talking about shared memory concept, then various CPUs connect with a single memory. In that case, we'll have data locality. And if I'm talking about distributed memory system, then again we have various CPUs and everyone have their own memory access only. Okay, so all these are your desirable attributes. So writing parallel codes. So for supercomputer, as I told you, we need to create various parts of a program, that is a module, basically different modules which are independent to each other. So we will gonna distribute the data to memories, because as we have to distribute code, we have to distribute data. That is why we need parallel coding or parallelism over here. So distribute the code of memories, distribute the data to memories, then organize and synchronize the workflow, and that is done by the slum processor, which I show you in previous slide. So according to this, we'll optimize the resources, whatever resource we have, for efficient algorithms and coding techniques. So these are our supercomputers. We have Param computer in 1991. Basically, it is in 1989, but just to get it in market up to date, it's 1991. So it's a Param 8000, which will I think initially in CDAC Pune only. Then we have Param 9000, that is evolved in 1994. Then in 1998 we have Param 10,000 with us. All these are updated versions. Then we have Param Padma in 2002 to 2003. Then next we have Garuda in 2005. Param Yuva is 2008. Then in 2013 we have Param Yuva 2. Then after this, various categories with us, that is Param Siddhi, Param Vidhi, recently Rudraksh. Now we have another one is Frontier supercomputer, which is highest with highest speed, latest computer in USA, California now. So basically, a supercomputer is nothing. It's a combination of various normal PCUs, as like we have in our laptop or we have in our house as desktop. But that must be the up to date, extreme good facility. So here you can see Param Shavak also. So here you can see one tagline also, that is NSM, that is National Supercomputing Mission. Inside this mission, AICT provide trainings recently also to become become the trainer for this high performance computing, and also for research part. So there are various frameworks or softwares which are used for parallel programming, because parallel programming, as I told you, without parallel programming, high performance is not easy. So For this, we have first software that is OpenMP, Open Multiprocessing, which is used for shared memory computers or shared memory systems. Basically, I told you that when one core wants to communicate with another core within a single node, in that case, we'll use OpenMP. And if I'm talking about MPI, that is message passing interface. We'll use it when a core of a node communicate to a core which is in another node. Okay, then another one is OpenACC, that is again as like OpenMP and MPI, that is used for computers for accelerator modes basically. Then here, what is in OpenMP software? Here we have one execution model. Its programming is extreme. It is somewhere similar to C language. You can see its programming on side by side over here, and the process going on in OpenMP with each command you can see on parallel. So over here we have first we start our main program, then inside the bracket whenever we give hashtag pragma omp parallel, this keyword denotes to this software that now parallel region start. Here parallel region means now various core working together, various process, various threads running at one time. So here in this diagram you can see initially we have master thread, then we have these thread distributed into various processes, that is known as parallel region. Now uh, after completing this part, we combine the information into a single one. And if you want to, if again there is something else for parallel region, then in that case we'll again distribute it, distribute to various cores. So here you can take this basically this OpenMP programming model is based on fork join model. In fork join model, what we have various master thread with us. We have one master thread, then various parallel threads with us. So parallel will divide our task into three A, B, C. Then we'll combine it together. Then if again we need to run it parallel, then in that case here you can increase or decrease the parallelism course basically. Like first we have three cores, then we have four cores, then suppose two had two that one complete their task, then two still remaining. In that case we can basically the funda between this behind this is that we can increase the course or we can decrease the course depending upon our task at any moment of the program. So OpenMP, the basic syntax is something like this. We'll start with our program as like C include omp dot h. Then again we have curly braces. Inside this curly braces will do our work. So this is an example basic syntax for OpenMP. So this is the picture from the OpenMP software only. This will look like this. So when you have stdio.h and omp.h, these are your header files basically. So omp just used to attach your OpenMP file over here. Then here you can see hashtag pragma omp parallel. This must be available in your programming whenever you want to run the parallel region with default number of threads. Here, as I told you, threads means your processes, means how much processes you want to run for this particular parallel region. So this is known as your threads. You may increase this processes or threads, or you may decrease this processes or threads. So this is our software, MPI software. That one is OpenMP. This one is MPI. So MPI, as I told you, when a core want to communicate, a core within a node want to communicate with a core which resides into another node. So in that case, programming is like this. It is little bit tough than OpenMP. The reason behind this is whenever a node wants to communicate another node, because both cores reside in different nodes. So whenever a core want to communicate with a core which reside into another node, in that case that core have to give their identity means from where I am, who I am, need to give everything. So that is why it will give their rank, it will give their item number, what is the message, from where it comes, everything. That is why this programming becomes little bit difficult than OpenMP. So these are top 500 list of basically supercomputers. So here you can see one is secure. Basically, the here Frontier missing. Although Frontier is the top one recently, which is from USA now, and speed is the highest for Frontier these days. So this is world's fastest supercomputer, Sequoia. See, this is previous one again. Till now, we have Frontier also available. If I'm talking about this Sequoia, then in that case, it is 16.32 petaflop speed with 1.6 million processor inside this fastest supercomputer. So next, all these are about HPC, high performance of computing. Here I'm telling you about the intersection part of HPC and quantum computing, basically, where we gonna use these two things together. So various places we have, like first we have problem solving synergies. If I'm talking about problem solving synergies, then high performance computing excels in handling large scale numerical simulations, modelings, and you can say quantum simulations and cryptographic challenges. So over there we'll use high performance computing and quantum computing together. Next, if I'm talking about hybrid workflows, then in case of hybrid workflows, quantum computing is uh, currently in the noisy intermediate scale quantum era and cannot fully replace classical HPC. Okay, so but we need hybrid HPC quantum workflows over here, where quantum processors tackle specialized sub problems, while classical HPC system handles the rest. That are become more relevant actually. Then we have simulation and emulation with us. So according to simulation and emulation, your HPC is used to simulate quantum systems and test quantum algorithms, which is critical for developing and understanding. So next one is your machine learning and AI. In case of machine learning and AI, HPC already accelerate AI workload. Already accelerate, and quantum computing might further enhance certain AI processes like generative modeling or maybe some optimization task also. Next, we have interdisciplinary approaches. So in case of interdisciplinary approaches, uh, quantum mechanics, linear algebra, or algorithm designs, all are core to quantum computing. HPC professionals with a background in these areas can contribute to emerging domain very easily. Next one, we have why HPC professionals should understand quantum computing. So we need to understand this. For this, we have future proofing skills, then collaborative development. So let us start with future proofing skills first. So in case of future proofing skills, as quantum computing matures, your professionals and expertise in both HPC and quantum concepts will lead the design and management of integrated systems, basically. Next one, we have collaborative development. In case of collaborative development, your industry leaders like IBM or Microsoft or maybe Google that are building hybrid quantum classical platforms. So whenever HPC professional quantum expert will play, you can say vital role in optimizing these systems, basically. Next, we have research and development opportunities over here also. Both technology need HPC and quantum. HPC professional generally work with the cutting edge R&D environments, where quantum computing is a growing focus area these days. So one is enhanced problem solving. Obviously, when we combine HPC and quantum computing, that can address your computationally just to open up new research areas and your new industrial applications, basically. Then we have how to build quantum expertise for HPC professionals, basically. So we already know HPC, but if you're moving towards quantum computing, in that case we also need some quantum expertise. So for this, we need some foundational learning. We need to learn quantum mechanics basics, linear algebra, and some quantum algorithms also. We also need to explore quantum programming languages, like Qiskit, Swig, or Bracket. So next we have its HPC quantum integration. In case of HPC quantum integration, we need to study frameworks like Qiskit runtime, running quantum workloads, all these things. So next we need hands-on practice for this. So for this we need emulators, or we can create quantum emulators and simulators available in HPC environments, or maybe on cloud platforms. Next we have networking and community engagement. In case of network and community engagement, uh, I think we need to participate in conferences, workshop, or where we need to get some exposure about HPC and quantum both. So next we have applications of quantum computing in HPC. So applications, basically quantum computing has potential to basically revolutionize your high performance computing by addressing specific challenges. Okay, here one of the challenges your complexity, challenges your scale, challenges your time constraint. So there are some key points. One is your optimization problem. So here optimization problem, you can take application for optimization problem is your logistic or supply chain. For you can take HPC systems over here also. So these are your optimization problems basically. Quantum, you can consider quantum algorithms also over here, like your quantum approximate optimization algorithm. You can take this as part of this optimization problem. Next you have scientific simulation applications. In case of scientific simulation applications, quantum computing excels in simulating quantum systems, making it ideal for problems in quantum chemistry and material science. So application for this is molecular structure prediction. You may also take its application as drug discovery by simulating various molecular interactions. Next you have designing new materials such as superconductors or maybe catalysts. So this is your again one of the application. Next one you have machine learning and data science over here. This in this application, your quantum machine learning could complement HPC system by speeding up AI task. Okay, so application is accelerating training of large scale machine learning models, enhancing your data clustering, classification, modeling. All these are your machine learning and data analysis applications. In case of cryptography and cyber security, you may have, of course, here you can cover up threats and opportunities in cryptography basically. It can also create quantum scale algorithms. Applications you may go for it testing and developing post quantum cryptographic protocols. Now, next one is your complex network analysis. In case of complex network analysis, your quantum algorithm can efficiently analyze large and complex networks basically. Its application may be social network analysis, biological network modeling, or traffic and communication network optimization. Next one is your weather forecast or climate modeling. Over here you have quantum computing, which have improving weather and climate models. So applications speeding up your simulation for atmospheric process or climate models for accuracy purpose also. All these are again applications. Next one is your energy optimizations. In case of energy optimization, high performance computing systems consume significant power. So in that case, your quantum computing can optimize energy, and its application, you may moving towards optimizing energy grids or usage in data centers, various advanced energy system simulation, and maybe it's designing. Then next is your drug and vaccine development. So in applications, I told you COVID-19 COVID-19 example already. So next one is your financial modeling. In case of financial modeling, HPC is already used in financial analytics, and quantum computing can further enhance complex financial models. So applications are risk analysis and pricing of financial derivatives basically over here that can use in quantitative finance. Last one is your high dimensional data processing. In case of high performance computing, basically your quantum computing can handle computations in high dimensional spaces, which is challenges for classical high performance computing systems. So application for this is real time analytics for large scale simulations. You can use it. Next one is your challenges in quantum high performance computing integration. So challenges, we have various challenges over here. Basically, whenever we integrate quantum and HPC, both are new areas, and both are very uh, whenever we integrate together, then there is something new, and that will change, or you can say change the world, or change the research area, change the fundamental work basically. So here we have various challenges, but whenever we integrate these two, we have various challenges. First of them, you can use hardware limitation. First of all, we have hardware limitation. Whenever we try to integrate quantum and HPC, then hardware limitation over there, which include maybe noisy scale quantum scalability issues we have. And then we have again environmental constraints also we have. If I'm talking about software and algorithmic challenges, then we have various lacking of standardization, basically frameworks. Then we have simulation bottlenecks. All these are basically constraints. Next, we have communication and data transfer. In case of communication and data transfer, we have you can take latency issues or requirement of bandwidth. All these are your communication and data transfer challenges basically. Then error correction and fault tolerance. Here we have problem, basically challenge in error rates. Then we have error also we have various overheads, which is in error correction. Then we have integration and workflow design. In case of integration and workflow design, we have challenges related to hybrid system designs, or maybe challenge in balancing the load. Then in case of resource optimization, here we can move with challenging energy. In case of energy consumption, in case of hardware utilization, both challenge in case of resource optimization. Then in skill and expertise gap, we have various knowledge challenge over there, talent challenge, because still people are not that much aware about high performance computing, not that much aware about it's not normal quantum and HPC, and integration is extremely tough. So for this we have to learn lot of things, which I'll show it to you later in further slides. So these are all challenges. Next, we'll move towards hybrid quantum HPC. So whenever we combine these topics, quantum and HPC, then a hybrid product material becomes, that is your quantum computing. Basically, it's not a universal solution, but rather a complementary tool in HPC. Here it is clearly mentioned that your hybrid system aim to leverage quantum and classical system strengths basically. So here we have some examples. Quantum processes can solve specific parts of optimization problems, while classical HPC systems refine or verify the results. Then this is our future outlook. We have quantum computing role in HPC that will grow as the technology matures, and the focus on hybrid quantum HPC system will likely define the next era of computational science, enabling breakthroughs in fields like material science, cryptography, and artificial intelligence. So, in today's lecture, our summary is all about the HPC parallelism course, scaling up the performance, increasing the number of cores, or increasing the number of CPUs, and how to relate it with a core. Then we'll how to accelerate these, where GPU use, where CPU use, then appropriate frameworks for these CPUs, GPUs, high performance computing. Then we'll learn how to interact HPC and quantum computing, what are the advantages, etc. Thank you very much, everyone.
Thank you so much, ma'am, for this incredibly informative and engaging session. Your expertise in quantum computing and its connection to high performance computing has provided us with valuable perspectives and practical takeaways. We are truly grateful for your efforts in breaking down these complex concepts into actionable insights. Your guidance will surely help us integrate quantum principles into high performance computing related research and applications. Thank you so much.
Thank you, sir. Thank you very much. Thank you, Amit sir, for giving me the opportunity for this talk. Thanks a lot.
Thank you, ma'am. Thank you so much.
Ji, sir.
Participants, we kindly request all the participants to turn on their cameras for a moment, as we need to take screenshots for documentation purpose. Before feedback, you can kindly turn on their cameras. Participants, please turn on their cameras for a moment for screenshot purpose. These screenshots are required to fulfill the guidelines of this FDP and to ensure proper record keeping. Technical team, please take the screenshots. Thank you, participants, for your efforts, for your enthusiastic engagement throughout the session. Please remember to fill out the feedback form for this session, which is available in the chat box. Your feedback helps us continually improve. Now with that, we wrap session 8. Stay connected as we continue this exciting journey into the realm of quantum computing and machine learning. See you tomorrow in the next session. Thank you.
Thank you, sir.
Thank you so much, sir.
Thank you all.